so this should be it. And then I will share my screen. And you should all be able, can you see my presentation? Yes, very good. Okay, yeah, welcome everybody. Very happy you've all had time today for our little project. We've called it so far the ACV Meetup, which stands for Applied Computer Vision. But if anybody has like a great name idea on how to update this, we're more than open for good recommendations. Before I start, I think for now that's a bit, here everybody knows me, but I'm Bruno. I work at SoundMap together with Mael and Aman and Jakub. And I've done my master in computer science at RWTH Aachen, with a focus on machine learning and computer vision, and I'm generally very interested in these topics. And so today, what I'm first going to talk about is a bit the idea and the format behind this meetup and why we thought this might be a good idea to create this. Then we will have a presentation by Aman on how we at SoundMap implement and use real-time plane detection. And then later on, you will understand when I explain the format of this, I will talk a bit about our problem at the moment, which is how to design an efficient obstacle detection benchmark. And I would like to finish off with a part of discussions, which should be somewhat the core part of this. Yeah, basically, why this meetup and what it should be about. So, during my time at university, we've had these reading groups, and when you look online, there are a lot of these also for if you're not a member of a university, but like groups like Hugging Face and others offer these things where you can join, you read a paper together, you try to understand the paper, sometimes implement it. And I think that's a great thing. But what I'm missing in this space is mainly there is no such thing. I've tried to find some over Google, maybe I missed some, but there's nothing public, which is quite famous, which is more or less famous, where you try to take these stuff from research and actually try to apply it to real world problems. So instead of saying, yeah, we're just going to run it on that one benchmark and we try to get this one nice score a few percent better, or we have this one fancy method which only runs if you have 8 GPUs at the same time. The main idea here is that I would like to talk about real applications on real data with its real problems. So stuff like how long does it run? Is it robust? Does it handle all the edge cases? And so on. These are things I want to talk about and want to, in the end, learn about as well. And this is why we would like to create this and see if this actually makes sense. This is not supposed to be something where we just read papers. Papers can be a part of it, but it's not supposed to be a paper reading group. And it's definitely also not a place where you can only present stuff that is finalized or camera ready. And this is definitely not something where you need the fully polished version of your projects. And so the format is basically, as like a suggestion for now, is we meet once a month, roughly, maybe decide on a date through Doodle or something. It's not supposed to be longer than 45 minutes to an hour, so that like everybody can fit it in their day. And we all have other things to do. And then basically the core idea behind it, it's supposed to be that somebody gives a presentation on something cool that he did in this area. So basically we will start off with this today. And then the second thing should be that somebody also is able to present a problem from himself. And then we discuss about this problem afterwards. And this, especially the area of stuff that you can present or the problem you want to talk about is quite open. So as long as it is somewhat related to computer vision or machine learning and in like some real world scenario, I think for the moment, I wouldn't make it restricted furthermore to what should be possible and what not. So that's basically the format we want to do this today. And I would suggest that we just give it a try today. And then afterwards, if we see it works or it doesn't work, or if somebody has a suggestion, we can update this later on. Yes, basically, this is the point where I stop talking and I'll give the word to Aman and he can start with his presentation.
Okay, thanks, Bruno. Here we go. So I hope you can see my slides. Yep. All right, so let's get started. So today I'll be presenting ground plane detection. So this is in the context of a navigation module. We've been building a town map where we want to tell the user, let the user know where they can walk and where they cannot walk, and in the ideal case, provide them with the direction, like an optimal direction to walk in. All right, so who am I? I'm a software engineer at TownMap. I just did my internship here, and now I'll be joining full time. I just finished also my bachelor in computer science at EPFL, and I'm also interested in machine learning and computer vision. Although this is my first real project with computer vision, so I'm really just getting into the field. So today I'll be talking about firstly plane detection, which is the main module. Then I'll talk about how we use the planes we detect to implement the navigation module. And then I'll talk a little about how we optimized from our first prototype to a model that we could actually use in a real world situation, because if it's too slow, then there's no use. And I'll show you some results at the end. All right, so firstly, let's start with plane detection. So the basic idea is so we have our depth image, which we have from an infrared sensor. And what we do is we basically divide up our image into superpixels. And for each superpixel, we perform some simple checks and the main part, which is the principal component analysis. And once we're done with that, we perform region growing, which is to merge adjacent superpixels into a single plane if they are similar. All right, so this is how a superpixel grid would look like. Uh, so the first simple check we do is to just check if a superpixel contains too many unknown pixels. So there could be multiple reasons for unknown pixels. One is that there is a problem with the sensor, or if something is hidden behind something else. But in either case, we want to say that that superpixel is not a plane, because either we're not sure. In that case, we want to be conservative and say no. And in the other case, it's just really not a plane. The second simple check we do is whether a superpixel has too much depth variation, because if it's varying too much in depth, that means it's not planar. So in the image here, you can see that, so this is a doorway, and when the door ends, we see that there's a huge change in the depth values of the pixels, and this would be detected in this simple check, and we would classify this superpixel, the one here, as not being planar. I'm not sure if you can see my cursor or not. Could someone confirm, please?
Yeah, we can see.
Okay, all right, thank you. All right, so that's the simple check. So if we have ruled out a superpixel as not being planar, then we don't look at it further. But for those which remain, we do this next technique, which is PCA. So PCA in general is something used in machine learning where you want to find directions. So if you have a huge data set, you want to find, which is a high dimensional data set, you want to find the dimensions which are the most important to explain the variation in your data. So in this is just a 2D example where you have these points scattered on a XY plane, and you want to find the dimensions which actually explain the most of the variance. So in this case, the first component, which is the most important one, would be this arrow, the bigger arrow, and the second component would be this smaller arrow, since it explains less of the variance. Now we apply this technique to a 3D point cloud. So the 3D point cloud we obtain from the depth image. So it just means like a set of 3D points in every superpixel. And we basically compute PCA on this set of 3D points. So what happens in this case is that since there are 3D points, we'll obtain three components. Now, if the points in the set, they all lie on a plane roughly, because there's always noise, then the first two components, the most important ones, are going to be along the plane, because they are the ones that's where the points vary the most, since they don't vary too much in the axis that is perpendicular to the plane. So most of the variation is going to be explained by the first two components, and the third component is going to have a very low contribution. And if that is the case, it will also be the normal vector to the plane. So this already tells us which superpixels are planar, And if they are planar, then we get the normal vector. So once we have these superpixels classified and they're plane normals, what we do is we look at adjacent ones and merge them into the same plane or not, depending on their normal vector's direction. So on the left, there's an example where the two planes are pointing in similar directions. So if you just compute, for example, the dot product of the normals, it will be close to 1. So we just threshold that dot product and see if they are similar enough. So on the right, you have an example where they would not be merged. And then we do this for a adjacent pair of superpixels, and we proceed in sort of a breadth first search fashion, starting from any superpixel, as you can see in this animation. And so what we obtain in the end is a superpixel grid segmented into different, so either some are just not non-planar, and then those who are planar, we have them divided into different planes. All right, so that's the plane detection part. So if you have any questions here, I can perhaps pause to answer them, or we can continue if there's no questions.
I mean, just to clarify this, as I think what we want to do is basically you have the cameras. The cameras are worn. Basically, we probably should have explained that a bit better. And so you wear the cameras, and then the idea is that we want to find out where is actually. So we find multiple planes in the image, and the question is where is actually the plane that we walk on. So assuming, for example, a table also has a plane, the ground is a plane, and so on. And so the first step, that's what we use to actually say, okay, before we can decide what is the plane we walk on, we first need to find all the planes that are actually in the image.
I have one question, but maybe this just comes because I'm not like too much in this topic. But if you have a camera that records an image, how does it translate to a 3D point cloud? Because I would say that, well, even though it's technically a 3D space that you observe, it's just 2D information.
So because in the depth image, you have the depth values which you can take to be the z values, and then where they lie in the image give you an x and y coordinate. And if you have also the focal length of the camera and the principal point, then you can basically transform all these x, y, z's into actual real world coordinates, which are centered around the origin is the camera basically.
Oh, okay, thank you.
I've got one question, but it's not an understanding question, but more technical. Should we keep them till the end, or should we do that now?
Just ask.
Yeah.
You mentioned in the principal components analysis, which, by the way, I never thought about using it that way. Quite cool. But you said that you use the third component as the normal of the plane. And as you mentioned before, the points on the plane are probably like noisy, of course. I mean, it's real data, it's always noisy. So I would imagine that because it's the third component, it's probably the very smallest component of the three, that this will be affected by the noise quite heavily. But on the other hand, you've got two components which are probably quite stable because it's the XY coordinate of the plane. Why don't you like take the normal to that one? This should probably be a bit more robust.
Because what you obtain, the three components you obtain are necessarily perpendicular to each other. So that would also give us the same result, what you're proposing, I think.
So they're always rectangular. Okay, I didn't know that.
Always perpendicular.
Okay. Thanks.
Yeah, I get a question as well. Maybe it was an understanding question though. So you lay a grid on top of the image, right? That's what you call superpixels, right? And then you find the plane via the principal component analysis for each of those superpixels.
Exactly.
And then the region growing again just connects the superpixels to each other based on the deviation of the normals of the planes.
Yeah, exactly.
All right.
I think one thing to mention here is also, so what Aman also tried is to not use a grid that has like fixed width and height. So we tried with superpixels that have different size, but that actually resulted in a lot more computation time. You will see that later, while not giving a lot of benefit in the overall result quality. And so that's why we, in the end, stick to like a fixed size for each superpixel.
Yeah. All right, so let's move forward. So we have got our planes. Now we want to identify the planes that are like that correspond to what a ground plane might look like. So they have their normals pointing upwards. That's just a simple way of saying it. So example, a table surface and the ground surface would have similar normals, and we would classify both of them as ground planes in the beginning, just for now. And then we'll obtain multiple ground planes, and we'll have to select which one we want to be the walkable plane. Then once we have got that, we have to do some processing and apply some temporal consistency, because we're doing this on a video sequence. So let's talk about that. So basically, once we have all the planes, we have to filter the ones which are ground planes by thresholding the normal vector angles. So we compute what a normal vector of a ground plane should look like by just experimentation and tuning. And we then use those thresholds to find what are acceptable angles for this normal vector to be considered as ground. Then to find the walkable one, we select the ground planes. So this could be one or more ground planes that are very close to the bottom of the image. And they are both ground planes, so not just planes, but ground planes. So we have got our walkable plane. And just so that, just as a extra check to see if you're not doing anything wrong, you verify that the plane is far enough from the user. So let's say if you are standing in front of a table which is very high, but it is still considered as ground, and it's still detected as the walkable plane because it's the closest to the bottom. Well, we won't say it's the walkable because it won't be deep enough. It won't be far enough from the user. So this criteria is only passed by actual walkable ground surfaces. So once we have got our walkable plane, which is a single plane, we have other issues to resolve with like shoes. So since we are using the bottom camera, we sometimes very often see the shoe in the bottom image, which kind of messes up the ground plane detection because the piece it's already rejected by simple checks, and if not, definitely by the PCA. And so on the left, you can kind of see what the output looks like without any processing. And the other problem is that so initially our users would like to, or we assume that our users would like to use a white cane along with our device, just before they get used to it. So we have also to take care of the fact that the white cane should not impact the results of our algorithm. So we remove this by. So first we tried a lot on detecting this white cane and just seeing, okay, we found white cane, let's remove it. But detecting the white cane is not a very easy task because there are many lines. So we tried Iou transform, for example, which detect lines, but we did not find anything which was very satisfactory. But in the end, we made a very simple assumption, which is that in front of the user, like this bottom center part of the image, we assume that it is always walkable. So the very small part just in front of the user. And once we make this assumption, we can kind of fill the hole, so all the holes which are protruding from the bottom. So all the obstacles like shoes or canes that are covered overall by a walkable plane, except from the bottom part. We basically fill those and assume that they are walkable. And so this, of course, needs more real-world testing, but in all the examples we've tried until now, it works quite well. And so on the right, you see the results where you do this whole bottom obstacle filling out. And finally, so just to also, I should mention that on top of this ground plane detection, we also implemented a simple navigation system where we want to go from the bottom center, to the furthest point we can achieve. So in this case, this white line indicates in which direction we should go. And with that, we have a small problem, a pretty big problem, which is that the output of the navigation module, at least, fluctuates a lot depending on very small details in the ground plane detection. Because in the image on the left, which is captured just 1 second before the image on the right, there's a small area which which lets you go further. So the navigation module chooses that as the best target destination. Whereas on the right, you have a completely different angle because of a small difference in the ground plane detection's output. And so these fluctuations, we want to avoid them. And the way we do that is we apply temporal consistency on both the ground plane detection and the navigation module. So the navigation module, we require that the angles are not too different from the previous ones. So to do that, we simply do an average over time of the angles over the previous frames. And for the ground plane detection, we try different techniques. The one we mainly use is the Iou consistency, which means intersection over union. So that just ensures that the plane we found in the previous image and the current image is similar enough. And if it's not, then we just use the plane we found in the previous image. So let's say the ground plane detection goes wrong for some reason and you detect a very small plane here, then the intersection over union of these two planes will be very small and we will reject the new plane. And we can also alert the user to just stay put, or we can use the previous one. All right, so that was what I had to say on navigation. If there's any question, I can pause here.
Just a quick question. Do you deal specifically with something like you'd already talked about the table that you recognize that it's not far enough away, so it doesn't count as ground, but the ground under the table, depending on how far you're away, will still count as walkable ground, even though technically you wouldn't be able to walk on it. Is that true, or is that an issue?
That is indeed an issue, and it depends on how much you can see under the table, but mainly because of the depth sensor. So as we had in this example, yeah. So if something is covered by another surface, the depth sensor generally classifies that as unknown because it doesn't get the infrared signal back. So it would detect a little bit under the table, like a small area, but then not too much that it becomes problematic.
Okay. And the closer you get, the less relevant the problem becomes, right?
Yeah, exactly.
I mean, on the other hand, if you can't see it, you don't know if there's, I don't know, a child lying there.
I think one thing we have to mention here is that we agreed on the problem. I mean, that's something, I mean, what this whole like meetup thing should be about a bit is that there is always noise. We won't have the one fits it all solution. We've just made some assumptions that we hope will cover, and a lot of the cases that we will counter. This is still a prototype. So this is the things you have to see on the side with this. I mean, for example, the assumption with the shoe and the cane that we can assume that the area directly in front is walkable has worked so far, I would say, very well. But obviously you can construct that one edge case that will break the system there. And the question is just, how do you deal with this? But so far, as this is something we haven't, which we just integrated into the next prototype, this is something where I would say we've just tried to make as little as possible assumptions, so to make it as general as possible, but the points where it would just, there are some where you just cut off like the 0.0 whatever % of edge cases that you don't want to cover because it gets too complicated.
I got a question. I mean, sure, superpixels, I kind of guess you use them for computational efficiency. Is that the only reason? Because I kind of can imagine that depending on where you have some small stuff in your in your area, that you will discard a superpixel because there's one small thing in it which will not pass the threshold that you mentioned in the beginning. But this will, of course, probably cause the noise in the navigation, or will actually, I don't know, disturb the region filling if you're unlucky.
Yeah, so I guess the solution is to like make even more smaller superpixels, but then it becomes computationally very expensive.
Yeah. Okay. And for the fluctuating navigation, I don't know. My naive guess would be like, what about a rolling average on the vector and so on? So that would be based on the assumption that the fluctuations are offliers that occur randomly?
Yeah. Yeah. So, sorry if I was not clear, but like that's exactly what we're doing.
Okay.
Yeah.
I also got a very short question. So about the hardware setup. So do you know the extrinsics of the camera? So what I mean is like, for example, the rotation of the camera, is it always fixed? So it's always like pointing downwards, or how much movement is in the camera?
I mean, it is worn, so it will be different for each person that wears it, but we know roughly how it looks. I will just quickly, I don't have one prototype lying around, but so basically how you can imagine it is like this. You have one here, one here, and one here. So one is pointing straight, one is pointing down, and one is pointing up. And I will show you some like real world examples later of this, which I finished today, where you can clearly see how the cameras are situated.
Okay, so it's like more or less, you know, that it's pointing downwards, one of the cameras, and then you do not have the problem that the wall is then misclassified as the column.
That's one of the assumptions we made, is that, for example, this algorithm is only run on the images we get from the bottom camera.
I see. Okay, great.
Okay, so I'll continue with the optimization part. Yeah, so first when we built the first MVP, it was very slow. I think it was not even running at 1 FPS. So it's completely useless if you want to use it in the real world. So now I'll just talk about what, like how we selected what to optimize with like which parts, and then how we optimize it. All right, so first a quick intro to Amdahl's law. Some of you might already know it. So what this says is basically if you have a program which consists of, let's say, two independent parts, A and B, and so A is in red, B is in blue, then you have basically two choices. First, you either prioritize optimizing B or A. And if you, let's say, make B 5 times faster, then you have made some progress and you've reduced your total time by this much. But if you had focused your efforts on optimizing A and you only, let's say, you only made it twice faster, not 5 times, then already you performed much better than in your other choice. So this just shows the importance of choosing the part of the optimization correctly. Like what should you focus your optimization efforts on? Of course, in the end, you want to optimize everything, but just in the beginning, and also like if some parts are just very small, then it's just not worth optimizing them, because even if you completely remove their significance, like let's say you in the perfect world they run in time 0, then even then it won't bring a significant change to your overall time. So how we applied this to our case, we used the profiling tool in Python, and basically found out which functions take the most time. So as you can see in this, this is the output of the profiler. It's C profile in Python. And so here we can see that the PCA function takes like 80 seconds out of 120 seconds of the total running time. So this is run on many images. I think, yeah, so 6,600 images. So the PCAs are responsible for around 65% of the total running time. So that's really something we should optimize. And if we can even bring it to half, it's already very good in terms of the progress we've made. So from here we have two ideas. One was to use this trade-off. Basically, instead of doing the PCA on the entire point cloud inside a superpixel, we choose a random fraction of the points. So let's say we choose a random 10% of the points, and then we perform the PCA only on those on that smaller set of points. And theoretically, it should give us the same results. And this is something we've also benchmarked. Like we tried different percentages from 10%, 20%, 50% to 100%, like how much we optimize. And the results we get are like basically there's no significant difference in doing this trade-off or not. So like using less points in the PCA or not. So that already gives us a good amount of optimization. And then we also looked for optimizations in the PCA coroutine we implemented, which was based on NumPy. So this part is about basically how we optimize this PCA coroutine. In the beginning, it was just like you compute the eigenvectors and eigenvalues of the covariance matrix of your points. So your points are in this text matrix. So I basically dug into the eigenvector function and the covariance function. And the coherence function looked something like this on the right, where like most of the function is just performing checks on the input. Like, does it conform to this rule? If it doesn't conform, should I change it? All these sort of checks that NumPy has to do because it has to deal with all kinds of inputs. And at the end, you just have two lines of computation, which actually produce the result. So since we have designed the whole pipeline ourselves, if we have done everything correctly, which you can verify by testing, you can be sure that the input you provide to this function is going to be correct. So you don't need all these checks. So what you can do is just take the last two lines and implement them yourself, and then call again. So you find the covariance yourself, and then we call this eigenvalue function, since that was not something we could optimize. And just making this change made this coroutine like 2.7 times faster. And if we go back, this was being called, this function was being called like around 100 times per image. So if we optimize this part by 2.7 times, we have optimized the whole pipeline. So not the whole pipeline, but like this part by like 2,700 times faster. No, sorry, 270 times faster. Bad at math. All right, so the next part was optimizing using Cyto. So Cyto is basically a language of its own, which is a superset of Python, which also allows you to use define C types and use functions from the standard library of C. And so this is the same function, which is a conversion from Cartesian coordinates to spherical coordinates, implemented first using NumPy and then using Cyto. And you can see it's the exact same code. And the Cyto version performs like 18 times faster. And if you're calling this function maybe 10 times, 20 times, or if you do this so we're doing this actually for every normal vector. So we do it around 200 times for every image. Then we make it like much faster. So yeah, that was the optimization part. If you have any questions, I can answer them before we go on to the results.
Just a short thing. I accidentally also supervised a master thesis, just as an advisor, where the topic was to replace the principal component analysis with a singular value decomposition. And I can't really tell you what the result was, but at least the guy that wrote the thesis had this idea, and I just wanted to ask if you also thought about this or if this is relevant for you.
Yeah, actually, I also tried that, and that gives better results than just the first line. But I think the last one we got was still better performing than SVD.
Okay, all right.
I also got a question here. So you're using NumPy here. So all this procedure looks very parallelizable. So you have a lot of superpixels, and for each of them you can do individual computations. So this screams for GPU usage for me. Did you try something of this? If you can also put this on GPU?
So basically we have 8 parallelizable. So I think we have 8 cores on our device, and most of them are being used. And we did not have any extra real estate in terms of cores.
Yeah, it's quite expensive to have this.
Just to give you an idea, so this is the where everything runs on.
Yeah.
And the GPU is already used. I mean, so it's basically a Raspberry Pi with a TPU, which is a tensor processing unit which Google produces. And the TPU is like very, very small, so you can load one model into it, and that's our object detection model.
Okay, I see.
So there's unfortunately no, but yeah, no, obviously there's a huge amount of possibilities if you have access to like a state-of-the-art computer. One thing to see is with the numbers from the profiling, you have to see these are the numbers from the M1
old version.
from Aman. Also, this is not the time it runs on the actual kernel that was on the production device, but these are the numbers from the MacBook.
Yeah, in general, it's I think 10 times slower than the MacBook results.
Yeah.
Okay, so if there's no more questions, I can show you a couple of videos that we filmed, one using a white cane, one using where we walk through a doorway. So let me share my entire screen. Ah, wait a second. Okay, so I'll probably do this. No. This. Okay, so I hope you can see the video. So just, yeah, on the left, you have all the ground planes we detect. In the middle, you have the walkable plane superimposed on the depth image. And on the right, you have the walkable plane superimposed on the grayscale image. And on the right, you also have this this white line, which shows like the best direction we choose for the navigation. And in this video, you also, this other line you see is the white cane, since we filmed it with the white cane.
What I would suggest is after this video, is that I just show you some real world examples, because so that you see that it actually works also in the real world.
Where was this? Was this not the real world?
Yeah, no, but that was our office, and it actually works also if you walk on the street.
The office doesn't count as the real world.
So there, what you see here is it as laggy as?
Yeah, it's somewhat laggy.
I will go through the images then. So what you see here is that we have our setup where we have the three images from the three cameras, which are situated next to each other. We have the one pointing to the top, we have the one pointing straight where the object detections run on, we have the one pointing to the bottom where we run the ground detection. And what you can see here, I hope it's not as laggy now, if I just slowly go through, is that it actually picks up quite, I mean, we have some like very slight minor problems here that her foot is not picked up, for example, correctly. But this is due to the fact that the superpixel have quite some size to avoid like overall the computation, or reduce the computation effort. And I think these problems are actually not that bad, because we don't want to give it like a centimeter correct navigation, but it's just to give it overall idea. And when you run it quite a bit, you see that it actually picks up quite well the left border. So there, for example, you can see it even understands like quite well that there is the entry to the doorway. The person is surrounded quite well. And if you go around, you can also see that here on the right, there is like a bumper. So cars don't go on the, it's like a, I don't know, cement bumper, whatever. And this actually picks it up also. And so we are able to run this at, the numbers at the top actually, these are the ones when we run it on the device, and you can see that it actually is able to, this is not the numbers from the device, this is from my computer, and but we're able to run it between 5 and 8 frames when you scale it down a bit, and you can see that it actually works quite well. In red, you see if there is an obstacle detected. And so, yeah, there is, I would show you the GIF, but that was actually kind of laggy. That's why I'm just going through like this. Yes, that's what I just quickly wanted to share.
Yeah, that's really cool. I actually need to go now, but thank you very much. This is really actually very interesting, because I'm very far away from all of this.
Okay.
Yeah, I'm looking forward to the next time.
Very good.
Bye.
See you, Paul.
This looks really cool already. Awesome.
Yeah, it's
I.
yeah. No,
Sorry, go ahead.
I also just wanted to say that also, I would say that we're, at least I was, I'm not sure about Aman, but I was very positively surprised how well it actually works. And the point that you have to see, it runs at a certain amount, like it is, the computation time is actually not that bad at all. So like we can reach up to 10 frames a second if we don't do anything else with all the other stuff like IO around it. It's more like 7 frames per second, which is still enough for our application. And so I think that's definitely something that's going to be at the core of the project, like at the core of the software for quite a while. And yeah, that's what I mean. This is basically what the first part of this was about. It was just to see, because I mean, we had, like, I've read many of these tutorials or stuff on the internet where people explained how they do stuff, and now we have been able to find something and produce something that is also like similarly cool, at least I feel like. And the idea was just that, like, we would like to share that a bit. And yeah, so that's how the format for the first part is supposed to be like. I don't know if you have more questions, just ask over.
Yeah. So what is actually the next big thing? So what do you want to make better? So what is the challenge right now?
The challenge in general for us, or just on the
for this ground plane. So what do you want to make better with this? So what do you think is the next step?
You want to say, Aman, or should I?
I mean, I guess the main problem is like the edge cases and assuming that, like, we make some assumptions to avoid this cane. So like if we, I mean, one option was to put some, for example, some stickers on the cane to really detect where the cane is. But here we went for the easiest solution, let's say. So in the future, that would be something we should keep in mind.
Yeah, I think this and like going further in this navigation direction on saying, okay, how do we actually use this to navigate a person around? And then, yeah, still, I think if we can make it more performant, that's even better, because then we can also try to run it on more than one image at a time. Or do we morph somehow the two images into each other to give it like a somewhat reasonable input? But I'm not sure how that was supposed to work. And so, yeah, these are the two basic ideas. It's like edge cases and navigation.
Do you actually do the obstacle detection completely separate from this? Or is it also based on intermediary results from this?
Yes,
Okay.
that's one thing. That's one big thing. I mean, the big idea why we actually thought about starting this is that in the old version, the one we tested in this summer, was that if you wanted to increase the threshold from which you detect obstacles, and you would go like to higher values, at one point the obstacle detection would pick up the ground as obstacle as well, and that would obviously ruin the whole results. So there was a natural limit to how far you can actually pick up obstacles. But now that we are able to differentiate and say, hey, this is ground, this is not obstacle, don't worry about it, we can actually increase the value quite a lot while still getting reasonable results. And those are able to, for example, start working on, okay, there we can already pick up, there's something 4 meters ahead of you. Probably you should worry about that, or something like this.
And I mean, you've got this approach with the planes and stuff and calculating the normals and everything for the superpixels, but do you actually, let's say, are interested in the 3D information, or do you just use the normals and then you are back to screen space, basically, where you just take the normal as an attached information to each superpixel? That's what it sounds like to me so far. Because like imagination is exploding maybe, but if you already try to find, like, what you're doing for the superpixels is basically trying to match the plane that fits it best, right? At least if you have not a lot of variation in the depth, because you have got these filters in the front as well and everything. But would it be feasible to actually, let's say, have also to expand this to not only have ground planes, but instead have a 3D environment in memory, of course, made up of planes, for example, which could help you in with the obstacle detection as well, because like an obstacle is just a big plane that I can run against, right?
Aman, do you want to answer this, or should I?
Go ahead.
Okay. No, basically, yes. I mean, this is just in this situation, we just limited to this one use case. But obviously, there are like a lot more possibilities to it. Saying that, for example, if you think a bit further and you just go a bit away from the obstacle detection, and we're, for example, looking for stairs or doors, these should, I think, especially stairs, should be something that at one point could be very interesting to pick up, because if you, for example, think of you walk towards stairs that go down, you have your plane, but then you have multiple planes, but they are not at the same level. Or if you walk up and then you see there, it's I think I would guess it's a bit easier, because you would have these like plane. you know what I mean, stairs, and then I think there we see some possibility to actually in the same process and in the same computational efficiency, pick up and understand where there are stairs and maybe doors as well. With doors, I see some more problems. And then I think regarding the obstacles, I see some problems in the sense that obviously a wall would work well, but most of the obstacles do not have planar surfaces. And so they, I think, wouldn't be, imagine like some plants or I don't know, yes, other things that are not planar. And I think there it wouldn't really work that well.
But of course, through your resolution, the things are always planes to your camera, aren't they? Because if you just like take 2 or 4 points and they are
not true. That's the thing. So maybe I don't know. Maybe we could like simplify to a point where everything becomes somewhat planar, and then. But the question is, would it then lose the information you actually need to differentiate there? Because at the moment our obstacle detection works quite well with just a simple or not super simple, but a simpler thresholding on the depth image, and we don't need to do any of the computation that is needed for the ground. But
of course, it is very tied to the use case, which makes it a little bit more efficient, especially on such a device. We also work with pies after all. So I've got one more question regarding the super pixels, and I mean the idea is quite nice, right? Because you basically group them up and only look at one point or one super pixel at a time and stuff. But they looked very fixed, right? So you probably had one integer that subdivides the image into even parts, and then basically on both axes, and that gives you your grid, right? I would be very interested in what happens if you actually can subdivide the superpixels. So because you've got a lot of edges, right? And the bigger your superpixels get, the less accurate your edges are, of course. But to not increase computing efficiency, computing time too much, it might be a good idea if you want accuracy to specifically look at the border of the superpixels that are bordering superpixels that are definitely your ground, and subdivide them further, maybe into 4 first, and check on those again. Of course, you have less points because the superpixel is less big, so the principal component analysis should also take a little bit less time and stuff like that. But overall, of course, it's more computation. So it will take more time, but I'm prudent to think that it will increase the accuracy a lot, especially for things like the cane, for example, which we saw in your slides, where in the later videos or images from Bruno, it seemed like you filtered out the cane very well, and it was always the superpixels were always somehow.
There was no cane in the.
There was no cane.
Sure, there was
really?
No cane.
Okay.
I walk without a cane there.
Yeah, but I lost track a bit. But
I see your point. Yeah, Aman, sorry.
Yeah, we actually tried something where we build the superpixels using k-means clustering, and the superpixels would kind of spread along the borders automatically. But yeah, that was very, very slow because of k-means clustering. But yeah, what you're saying, we haven't tried yet. And but yeah, the question is like if we really want that accuracy, because what we want in the end is just some rough boundaries and roughly knowing where to go.
Yeah.
Like we don't really at this point we don't really care if we got the exact ground plane or not.
Yeah, I think in this point here, it's really important to see that the obstacle detection, which relies on the ground plane detection, is the core part of our product in a sense. And there is the speed at which it runs is one of the most important things that we have. And so just improving and going from like 8 to 9 frames per second, it might be already worth it just to ignore these kinds of small, subtle accuracy improvements. But we obviously try to keep that in mind, saying, and that's something I wanted to show in the problem. I might shorten that a bit down because we already talked for 50 minutes, but that's something which we try to keep in mind while still saying the priority number one is the trade-off between runtime and quality.
I mean, I get why you're doing that, and it's totally understandable. So then my question would be, you plan on keeping the navigation based on the ground plane, or is this just for now as look what you can do?
No, this is the navigation is that's I would say more in like an experimental stage still, because obviously there's so many more parts to it. But this was the first, let's say, the first step for the navigation is basically okay, where can I actually walk? But all the other steps are not implemented yet, so that's why it still shows something there. We just implemented the navigational decisions on the.
So the jittering navigation error for now is just caused by how the current state is.
Yeah,
it's not a problem that you're currently tackling as a focus.
No.
Okay.
No, I think from the results I showed, the focus is more on giving like the best possible obstacle detection.
Okay, makes sense.
And improving this there. And then the next step, which will probably take a few more months, will be once we say, okay, obstacle detection is solid, all the other things are solid, then we go in this navigational part in there. But there are so many more problems arising from this that yeah. Okay. Do you have any more questions or suggestions or remarks on this?
I just got a very crazy idea in my head. So
okay.
To bring the performance stuff to the absurdum, is it possible just to you always have the super pixels to do this, to do a downscaling first on the image? So you have the super pixel and then you take the mean of the points in it. And then you just look into the, I don't know, the four neighbor mean values you found, and then calculate the normal from these 4 points only. This should be super quick. Then you don't have to do any PCA or
Sorry,
just
so
before.
So you find the normal how? I am not quite sure.
So that you have some kind of spatial downscaling, like that you put your super pixel grid on the image, and then for each of these grid cells, you calculate the mean value of the depth. And then you can just look into all neighboring points you calculate, mean points you calculated, and then you can calculate the surface with this alone.
So you mean, for example, if you had like 5 points, if you take the cross, or 9 points?
Yes, right. And then for the middle point, you can look at your four neighbors, and then you calculate the surface. This is super coarse for sure, but
yeah. The question,
if it's
what
just
I would
for
see is that, for example, I can show you some images where I think it would. I think that the problem is that this would break at the when you don't want, like when you have a bit more subtle changes in the ground.
It's probably also prone to noise more, right? Because if you have like I can imagine that the plane approach is getting rid of more noise than this approach would maybe, but that's just conjecture.
You would have to filter out all super pixels that have any disturbance in it. Like the first step you did, where you have a threshold on unevenness. I mean, that's totally understandable. But if you would go for this very course, you have to throw out everything that has any unevenness in it, because it would screw up the complete plane.
Yeah. But that's something that's true. I mean,
Small
we could
things
try
on
that,
screen.
but
Mhm.
that might be, yeah. To be honest, I
Could take the
don't
median
know.
pixel.
I don't really have a strong intuition on this, but yeah. Okay. Yeah. So that was it for the first part. The question is, as we're already 1 hour in, I would suggest we skip the second part for today. Or I can give a rough, very quick introduction on what I was thinking about it, then we don't talk about it, and then we talk quickly about the format, and then we see if we want to continue this or not. I mean, if anybody, do you have a timing thing? I could give like 5 minutes, just quickly what I thought we could do, and then
You're keeping me away from work, that's fine.
that's Daniel, for you always this is easy. Okay. Yeah. So basically, second part. The idea here is that this, I mean, for today that's us, but generally here anybody that wants can share one problem he had. I mean, basically the idea around this whole thing was me calling Daniel and Jonas about the cane detection and being like, hey, I have zero clue how we should do this. Do you have any ideas? We have a bit of a different problem. I think I can skip this now because that's something I already talked about a bit earlier. Basically, the state of the vision systems, if you like very raw overview, is that we acquire the images, and then we have two things that run in parallel. So they're decoupled from each other, which is the obstacle detection based with a ground plane detection, and we have an object detection and a tracking. And then we have a system that prioritizes the input and gives feedback to the user. And one thing that we're currently starting to work on, and what I personally think is one of the core things to us later on, is that we want to get rid of this, like we change something and we visually control if it actually made the things better or not. Because this has a lot of problems, like you can't look all through all videos. It's time consuming, it's error prone. And so the idea is that we want, for each vision system, we want to have it like its own benchmark with its own metric. And what it will bring us is an easier development and a control of minimal performance through the option to have like an iterative development process where you change something, you run the benchmarks, you see how it compares to older versions, and then you see how that works. And then the more important point is, because the different vision systems here depend on each other, you can also see what is the downstream performance effects you can have when you change one system in the chain. Does it actually, for example, it could be that you improve the performance for your one system, but the downstream part, so what I mean is tasks that rely on the data from your system might have a negative impact on performance because you changed some core idea behind it. And this can be quite easy for tasks that are well defined in the world of classical computer vision. Think about object detection segmentation with an IOU metric, or object tracking with a HOTA or MOTA. And the problem here is what happens if you design your own task, which nobody has worked on before. How do you actually evaluate this? What's the benchmark here? And so the problem here is what I showed you before with the little red areas. What we do is obstacle detection, and that's one core thing. But the problem is, how do I measure performance for this? What is the metric that actually captures the core difficulty of the problem? And how do I actually capture and annotate ground truth data that I can use to evaluate this? And so just to give you a quick idea, I mean, you've seen it before, but what we do when we do obstacle detection is, if you break it down into one sentence, is that we detect all obstacles that are closer than a certain threshold. Here you see an example where I walk in our office, and while you do this, you want to do two things. You want to ignore noise, which is quite a big problem, and you want to ignore ground to allow what I explained before, a threshold that is actually farther away than the distance from the camera to the ground in front of you. And one additional thing that we need is, we need not only that the knowledge of that there is an obstacle, but also a rough direction where this obstacle actually is. And so basically the idea at the moment is we take a cell-based approach where we lay different amounts of cells over the image, and then we get as an output the minimum distance to an obstacle in each of the cells. So you can imagine the more cells you have, the more fine-grained it is. And so our current situation is basically we have a lot of raw video data, which is noisy. Especially the depth is quite noisy, as you've seen. We can run our method on all of this, but what we don't have is one, a metric, and two, ground truth data, because you can't really trust the depth data that we have, and it's very hard to annotate, because when you see the color image, how do you know if it's now, like, let's say the threshold is 1.2 meters. How do you know if something is 1.3, 1.1, whatever? And then the second thing is, I mean, obviously you could just compute the contours of all the obstacles. Let's say we have ground truth data from somewhere. You just compute the IOU and have a metric. But is that actually the metric that boils this benchmark to the core problem we have? Because my core problem is not finding every pixel that is an obstacle, but my core problem is that actually all the important obstacles are picked up and are found. And they actually found with the right distance. And so the open question here is, what would a capturing or annotation or system look like that would solve this problem? And that's one of the problems we have at the moment. We have one simple idea, which is we take our color images and estimate the depths through the biggest deep learning model we can find, because this is a task we can do offline. And so there is an approach from, I think it's the Intel group, and they've produced a model that is called Dense Predictor Transformers or something, DPT short, where you can actually estimate the depth from a monocular image, which, for example, here at the top, you see works rather well. At the bottom is okay, but doesn't really work that well. And the problem is they also don't output the actual real distance. They just output a value which is in an inverse depth, I think, but we haven't been able to convert this into actual like centimeters and meters. And so, yeah, that's a bit the problem I wanted to talk about. I think that's a bit too much for today. If you have like some rough ideas, we can discuss.
Yeah, what you can like just quick thing. I think for the actual output of that model, probably it will rescale based on the content of the image. I can imagine that the nearest point is 0 and or 255, and the farthest point is the other one. And maybe you can try estimating actual distance for just specific parts of the image. Maybe you find some system that can do that for you, and then you can basically rescale these values 0 to 255 to actual meters, because you kind of need a ground truth within the image or something to scale to.
Yeah, that's the one. I mean, this is something we just started recently, and then we put it a bit on pause to figure out some other things. But I mean, yeah, that's definitely one problem, one idea we had as well. I don't know how well it works, but then you see, for example, if you take the bottom image, I mean, it's a very difficult image because, I mean, the sun shines in the camera. You have stuff that is very far away. It's already kind of blurry in the input image. Can you actually trust those results then? And I mean, I know there is probably the only perfect solution would be to buy like a very expensive depth camera and put it on top of whatever we use to film.
That was my idea.
But it was also the question is like, what is feasible for us and what is the least work for us? So that's a bit the problem we have at the moment.
Are you already outsourcing your annotation tasks, your labeling?
Not yet.
That is very recommendable, let's say. You
No,
still know. You were also labeling or not?
I was also
A lot.
labeling it. Yeah. No, but I think in this case, I think if you had the ground truth depth, you wouldn't even need a hand annotation because you could just compute the ground truth data from the image. But the main problem arises here from the noisy noisy depth data. And the question is, how do we avoid this, go around this? One idea I also had is we still have the depth data, and obviously we do rely on it in like when we use the device, so it has to be at least it has to be good somewhat. So the question was, what if we just combine these two? So what if we take the estimated depth from the DPT model, and then take our actual depth, like the depth we recorded, and then combine it in a sense that we know, okay, so for example, what you see here is you don't have all these shadow and black patches where something the infrared sensor didn't pick up that well. So what if you, for example, take the regions from the DPT model and the values for the specific regions from the recorded depth, and then combine this into something that is more closer to.
Is it really closer to the truth though?
You take
Because
noisy data in a noisy model.
if you have two outputs which both have an error, and you take, let's say, the mean for every pixel, then it will be worse than the better performing one of
I
the
don't
two.
know. That's
What
why
about a
we
laser
talked
scanner?
about it. I was hoping that you have a good idea. A laser scanner. I don't know.
I mean, you just need, you don't want to have it continuously, but you need, for benchmarking, you just need, like, I don't know, 3 different scenarios where you have the ground truth data, right?
I mean, the problem here is that at one point, so the thing is to just explain why this is so important for us, because you could always, this obstacle detection, do somewhat per hand. But the problem is that we classify as a medical device, and the medical device regulations are very, very, very strict when it comes to software updates and how can you actually ensure that the device works as it is meant. And if I write in there, so the obstacle detection, which is the core of it, we usually let one of the interns control it by hand. They're just going to come and chop my head off.
No, but that's exactly.
Yeah.
I mean,
but the thing is, I think the problem here is when you come, like, I think we would need at one point 20, 30, 40 sequences where we can just run it automatically. But if we take a laser scanner, we would need to redo all of these sequences.
Why? Why?
Now, because we need to record them with the laser scanner, right?
Yeah, okay, but you have to record 20 sequences once.
Yeah. So, but what you would do,
I think Bruno was just talking about the already existing data, right?
Yeah, I would love to take the already existing data.
Okay, you don't want to record new data. All right.
Yeah. But like the point is, that's something I don't really know what is on the market there. For example, I don't know how a laser scanner, if it works precise enough to give us actually the, and if it's super expensive, and like, do you just put it on top? Yeah.
Depends.
They're expensive as hell, but they're precise as hell.
Yeah. I think if you, for example, think about like how the data for all these autonomous driving data sets is captured.
That's LiDAR.
They take a car,
exactly
and they put like a shit ton of sensors on top, and then they know where each sensor is positioned, and they can compute actually the true depth value of everything.
So what you need is a fixed transform between your camera and the laser scanner, so you know exactly what point in the laser scanner corresponds to what point in your camera.
Yeah.
Should be as close as possible to not have different point of view.
Yeah.
And then you can map that.
Yeah. Yeah, I guess that's my hope was we talk about this and somebody has the genius idea to
magic.
I mean, if you have noisy data, you cannot make perfect data out of it. That's it. You need better data than what you can compute.
One thing maybe is you are talking about validating the object, not object, obstacle, the obstacle detection, right? And for you, an obstacle, you defined it somewhat according to your implementation. You know, you said, okay, it has to be this far away, and then it's basically an obstacle. But like, if you I think that's harder to validate because it depends on your implementation. If you can validate a step before the actual obstacle detection, and you can prove maybe that your obstacle detection will always work with that percentage in accuracy if the input data at some other point has a certain accuracy as well.
Oh yeah, that's
then you could validate only the first part, which might be easier to validate, and then calculate the accuracy from there.
No, that's actually a good point. I think, I mean, no matter if we say, I think this is interesting in the sense, regardless of how do we actually validate the obstacle detection itself, but obviously that should be a step in the validation itself as well. Yeah, so that's basically the problem. Unfortunately, I do have to leave in 10 minutes, and I wanted to talk about 2 more things before. So yeah, that was basically the format I was looking for. And also, I mean, so far the results were, I mean, we talked a lot about it. I think Tarek had a very good idea. Daniel had a very good idea. That's also what I wanted to get out of it. But now this was just from our perspective. And the question is, do you guys think that's something you would like to do again? If in the same format, in a different format, could you imagine that you have problems that you would like to discuss in this environment, surroundings? Is it okay if we invite a few more people? And all these questions regarding the format.
Yeah, maybe one thing that I noticed, especially about the first part, was that it was really basically just a presentation of something that was there, right? And I personally failed to see like a real problem that my brain could.
No. The first one was supposed to be just a presentation of something that is really finished.
All right. So the problem part afterwards, for example, that you just presented.
It should be a mix out of like or somebody shows something cool that like probably other people can actually use already. And then the second part would be, okay, hey, this stuff is not working with us. I mean, in this, like our problem now at the moment was not like algorithmic, but more like, let's say, more concept-wise. But for example, I already have some ideas for algorithmic problems next. I mean, I don't want to be the one that always presents. I can do this, but I don't need to. So, yeah.
Yeah, I agree with Tarek there. The first, I mean, was definitely interesting. But if we want to stick to 1 hour and something, then it doesn't make much sense to have like 40 minutes of it just listening to agreeable, interesting stuff. And it was presented quite really good and short. But you can maybe try to boil it down to like 50 minutes, like very no questions asked, just pop, and then afterwards have an open discussion, and then maybe go fluently into some open problems.
No, totally. I mean, we could do that. That we just say, we also say, okay, not so many questions, few at the end. We like make it hard cut at like 15 minutes and then go to the open things.
That would be nice. Apart from that, more people, sure. And unfortunately, I don't have any problems because I would like to work on that, but I don't.
Okay. Yeah, I mean, for now, maybe. I mean, this is something that is not supposed to happen every week, and whatever, probably in 2 months, 3 months, it's something different, and you have something. I mean, it's supposed to be one problem and one presentation each month, anyways, and that's not a lot. So I could fill that until Christmas easily. And so,
Yeah, I would definitely like to bring also the Mohammed, which is our new CV guy, next time. I think it could be interesting for him as well. And I'm not going to volunteer for the next one yet because I don't know yet. But
then what I would suggest, Jonas, do you want to say something as well? Or do you just agree? Jonas? Yeah.
I didn't understand the name. Sorry. No, I totally agree. So right now, I wouldn't also have something to present, even though I would like to also work on such applied stuff. But yeah, I'm definitely here for listening and discussing this. This is a really cool concept. I like it.
Yeah. What I would suggest then is that you guys, if like Tarek, some people from your company, but also if you have other people in the church that might be interested in this, Jonas, I don't know if you know somebody, Daniel as well, We opened this up to probably something where we are 20-ish, I would guess, for a first try. And then I will probably make a mailing list where you can sign up the next few days, so then you can send this around. And I would say I will look for somebody, if we find somebody that wants to do a presentation or a problem, and then if we can't find somebody, we will do that next time as well, and then look that we find somebody for the presentation afterwards, somebody else that does this.
Just a remark from my side. I mean, even if I would be working on something like that, I would definitely not be allowed to talk about it. And I imagine that if you don't have a private project, which is interesting, which if you're working full-time might be hard, I would imagine that this goes for many people working in this field. So what maybe is more promising if you try to contact like small startups like yourself in a similar
obviously
problem, and then the companies themselves attend.
Guys, show us your latest autonomous tech.
Yeah, exactly. I would get beaten the hell out of me if I would start talking about my projects here.
Same. So yeah, maybe we can also just, I don't know, I can ask Thomas or something whether there's some wish we can fill out or something similar to an NDA or so, and then we can just talk freely.
Yeah.
Cool.
Yeah.
Okay.
With official company recognition, that would be better.
Something.
Okay.
Bruno, wolltest du jetzt noch gleich über was reden oder nicht, weil du meintest, du bist gleich weg?
Hast du morgen Zeit?
Ja.
Ich schreibe dir nachher. Yeah, thank you very much for joining. I hope that was nice for you as well. I will send out some more information, and then probably, don't know, I think Slack channel is a bit too much, but like, so find a way where we can easily communicate, create a mailing list, and then we can see from there. I hope that we find other companies that can, like, I mean, derive a small part of their thing that might be presentable, might be at one point we find somebody from an open source project or so on. I will just give it a try and see.
I got one. I will send the name to you.
Yeah, maybe this. I don't know. I mean, in the end, I just think that like it makes the whole thing easier for everybody if everybody gives like a bit of knowledge. I mean, this is not our whole system. We just gave one part of it, and I would just like to keep it this way. But we'll see. If it works, it works. I mean, this is a try, and then we will continuously re-evaluate if it works or not. I would suggest. Okay. Perfect.